Welcome to Chem Help ASAP. Let's learn about polarizability and how it affects nucleophilicity in SN2 reactions. On the screen we have an abbreviated periodic table on the left. The atoms in this part of the table are the ones that we most commonly see as nucleophiles in SN2 reactions. Let's look at the halogens. Of course, when we talk about the halogens as nucleophiles, we're actually talking about the halides, anions, fluoride, chloride, bromide, and iodide. We have observed trends in the halides in previous videos. As you move down the periodic table, the ion gets larger, more stable, and less basic. We know that anions can be both bases and nucleophiles. If basicity decreases as you move down a column, then nucleophilicity probably does the same. Well, no, nucleophilicity actually increases as you move down a column. The same is true for the group 6 elements. Let's focus on oxygen and sulfur, and they're in the upper right corner. Alkoxides, oxygen anions, are more basic than sulfides, or thiolates, the sulfur anion. But sulfides are more nucleophilic. In fact, when we learned about SN2 nucleophiles, we said the alkoxides are good nucleophiles, but the sulfides are great nucleophiles. The difference is that alkoxides are more basic and will perform an E2 on secondary halides. Sulfides are less basic and therefore able to do an SN2 on more hindered secondary halides. Moving down a column increases nucleophilicity and reduces basicity. What's going on with nucleophilicity? Here is an alkoxide, RO-, and here is a sulfide, RS-. I'm trying to show with these circles the electron density. The sulfur anion is bigger because it is in the third row. Bigger sounds like a reference to sterics, a bad thing for an SN2. In this case, though, bigger is not adding bulk. Instead, it means the valence electrons in sulfur are further from the protons in the nucleus and less tightly held. When close to an alkyl halide, and we are using methyl bromide, the partial positive on the carbon attracts the valence electrons of the nucleophilic atom, so on the sulfur. Let's try to show these sulfur electrons moving towards that positive charge. This is a distortion of the electron cloud, and it happens more prominently in sulfur than it does in oxygen. Oxygen moves quite a bit less. I call this a distortion of the electron cloud. The more proper term is polarizability, which is the title of this slide. Bigger atoms have a more polarizable electron cloud. Soft is another term people use. Sulfur is a soft nucleophile. That's a good thing in a nucleophile. Oxygen is a relatively hard nucleophile, or less polarizable nucleophile. Hard nucleophiles tend to act like bases. The same trend is apparent with nitrogen and phosphorus. Amines are good SN2 nucleophiles, but often do E2 reactions on secondary halides. Phosphorus nucleophiles, like triphenylphosphine, can do SN2 reactions even on secondary halides, although the reaction is much slower. Nitrogen is smaller, less polarizable, and more basic. Phosphorus, one level down on the periodic table, is larger, more polarizable, and more nucleophilic. Polarizability is an interesting property related to atomic size and can help us understand the relative reactivity of SN2 nucleophiles.